Next, we're going to talk about peptide bonds, and this is how amino acids will bond together to form the larger polypeptide and eventually protein structures. And I think it's worth pointing out that when we just have a few amino acids together, we'll call that a polypeptide, and when we have a really much larger and structurally defined structure, then we start to call that a protein. And so one thing about the amino acid structure is that you're often going to see it in the Zwitter ionic form, which is a fancy word for having a positive and a negative charge on both parts of the atom at once. So the nitrogen bears a positive charge and the oxygen on the carboxylic acid bears a negative. And this is how the amino acid exists in regular pH solution, right? This is the more commonly found form. But it is a little odd to look at on paper, so you'll see the uncharged version of the amino acid as well. But I think it really draws attention to the fact that these things want to come together, right? We have an area that's really mostly positive and an area that's mostly negative, and when they bond together, it does relieve some of that. And it's not to say that it's the negative that attaches to the positive. That's not correct at all. But it just highlights the fact that these amino acids do want to combine. The side chains often have charges as well, so you may see other charges besides these two that are on the amino and the carboxylic acid side, but it is worth pointing out, and it is just to reconcile some of the other structures you're going to see. In any case, when we form a peptide bond, it's much easier to view it from the uncharged structure, as this is where we are going to take the OH and the H, and we have the following reaction, where the OH from one carboxylic acid side and an H from the amine side will come together to form a peptide bond with the amino acids, and this is an amide. That's another type of functional group, and an amide is characterized by a C double bonded to O, so there's our carbonyl, that's bonded to a neighboring nitrogen. This is a really characteristic structure of the peptide bond. And here we see this same kind of reaction that we've seen a lot of times before, right? What type of reaction is this? What's created as well when we form this peptide bond? Go ahead and pause here and see if you can determine that. This should really be evocative of the other biochemical reactions that we've seen in the lipids and the carbohydrates chapter. All right, hopefully you're able to determine that what is removed from these two amino acids is water, right? We have another dehydration reaction, and this theme of connecting biomolecules creates water, and separating biomolecules requires water continues to be true here for the peptide bond. And when we have peptides come together, we can make large structures, right? We don't have to stop at a dipeptide that we saw previously. Here's a tripeptide, and we have starting at the N terminus and going to the C terminus, because there'll be an amine side that isn't used from the first one and a remaining carboxylic acid that isn't used from the last amino acid. We can name this tripeptide, and it's from alanine, phenylalanine, and aspartic acid, so we'll name this ALA-Phe-Asp, right? That's the way that we could say the order of these amino acids, always from N terminus to C terminus. And note here that the third amino acid here, this aspartic acid, this has a charge. This has another COO minus on it. This is another carboxylic acid that's deprotonated. We will see charged groups on these side chains as well. And as we move towards protein structure, we'll see that this defines the structure of the proteins also. Larger polypeptides, we're probably going to start omitting the side chains that aren't totally relevant, or all of them, just to show the sequence. And so for something that's like 10 peptides long, we may want to just show it something like this, right? Gly, ala, ser, val, lu, lis, thur, phe, asp, tir. This corresponds to the different amino acids that are here. Remember, we have these 3-letter codes, and it defines the larger polypeptide from N to C terminus. Finally, the order matters, right? We need to go from the N to the C terminus. That's the order in which we're defining these polypeptides. And to bring this to light here, right, here is alanine and serine. And we're going to add them together with alanine first, then serine. And if we look at this final dipeptide, we see that it's the alanine that has no OH on its R group, right? The R group for the alanine is this H3C that's shown on the middle carbon. Serine is flipped upside down, but its R group is that CH2OH group, right? So different R groups. We have the amine, we have the acid, and that middle carbon will contain a hydrogen and the R group. So here, right, we have the R group of alanine that's left on the N terminus. But if we change the order and we add serine first, well, now it's going to be serine's R group that's left on the side with the N terminus. So we have two different dipeptides, an alanyl serine, ala-ser, or cerylalanine, ser-ala. So, creating these, and really being, a complete protein scientist, that takes years. The real important point, though, is that we go from N to C terminus, and that the order matters. We can make two different dipeptides with these two amino acids.